So we spoke about correlation in the last lecture, and we're going to move on. We defined correlation, we gave examples of correlation, especially of the problems interpreting correlation, which are rife. And the next thing we're going to move on to are the regression models. Now you can have a range of regression models. The ones we're going to focus on are the linear model. But these are statistical models, and they are incredibly useful. So if we had a correlation coefficient, before we spoke about the Pearson's correlation coefficient, that ranges from 1 to -1. It tells us the relationship between x and y. It can tell us if the relationship is linearly positive, linearly negative, or if there's actually no linear correlation between the two. And that was the R of 0. It can tell us how well those two co-vary in a linear manner. So if they are perfectly linearly correlated, then we have an R of 1. If they're negatively correlated, when x, and we saw why that happens. We looked at the equation of x times y, and because if both of them are positive at the same time, we're going to have a positive value. If both of them are negative at the same time, we're going to have a negative value. But if one is positive and one is negative, we're going to have a negative value. I think I said it right. So positive, positive is positive, negative, negative is positive, and negative, positive is negative. And if you have a range of those things, I mean, like if the dots are doing whatever they want in a space, you'll end up with a sum that's around 0, which is no correlation between the two. But actually, what we're getting is that there is a correlation between the two. We're not getting, and we're getting the direction, but we're not getting information about the slope. How does y change as a function of x? And now remember, another thing that's important about the correlation coefficient is that it's incredibly symmetrical. It's symmetrical. So x is correlated to y in the same way, exactly the same way that y is correlated to x, which is a problem in interpreting correlations, is actually we don't know who's the cause of the correlation. But if we're interested in knowing how does y change as a function of x, what we're talking about as a model is building some sort of model of, in this case, a function that tells us how y depends on x, and these are regression models rather than correlations. So in a simple linear regression, okay, simple as in y is a function of x, there is one response, there's a response and it has one predictor. Hold on, sorry. Then we have, in a simple linear regression, we have two continuous variables, so it's a bivariate regression, 2 by. We have an x, and this time it matters who x and y is, because y is the function of x, and x is our predictor. It's an independent variable, and y is the response variable. So if I can think about x is the temperature or the latitude, and or whatever other element, whatever other factor can influence y, which is the abundance of a species at a certain location. Okay, so we have something that's measured, a dependent variable, and something that is the predictor, the x. Okay, and y, simply put, is a function of x. Now in R, you'll see this as the function is called LM, which comes from linear model, and we have y, okay, our response, as a function, this little tilde thing here, is as a function of the predictor. So our model, simple linear model, looks like this: LM, open bracket, y, whatever our y is called, as a function of x. Okay, so y, function of x. Now the very simple linear model is something you know very well. It's the line, and we have y as a function of x, and this time the function of x is mediated by two parameters, and these two parameters are the slope, how much y varies with every change in x, and what we call the intercept, that the place on the y-axis where the line crosses. Okay? Now, many of you would have seen this the other way around earlier at school. It would have been ax plus b, where a is the slope and b is the intercept. In maths, now that you do fancy maths, it's this way. Okay, so b, or beta, is the slope. Now, what I know about y and x here is that the relation is linear, because b, the slope, is constant over x's, over time x. Okay, over all these x's have exactly, if I put little triangles up here, all these x's have exactly the same slope. So the relationship is linear. It's not changing in its slope. And what I know is that when the slope is positive, when b is positive, I have a relationship that as x increases, y increases. If the slope is negative, as x increases, y becomes more and more negative, okay, or more and or smaller and smaller. And I know that y does not have to be 0 when x is 0, and that is what the intercept is telling us. So here we have an intercept of 0, so it's crossing the not point, but it can cross anywhere. Okay? And there's actually a test that we get that tells us whether this intercept is different to 0 or not. And another thing that's really important, that there is, for every x, there's one solution, one y. Okay, one y for every x, and I don't have x's that don't have a y. Okay, so I don't have any gaps. And that's what the linear model is. I can have nonlinear models. There's a range of them. Okay, all these things can be written as a function, but these are nonlinear models. So we don't have the equation of the line. We have y that is a function of x, but not in this format, not with these parameters. It's not the straight linear model. Okay, so a nonlinear model, an NLM, is any relation between y and x that is not a linear relationship. And in those cases, we can have, for every given x, there could be more than one y value, like here. Okay, this x has 3 y's associated with it. We can have gaps, we can have areas, especially around the 0. You know, if it's 1 divided by x, right, I'm going to have a line here, I'm going to have a line there, but there will actually be no 0 value. So I can have gaps. Okay? So these are nonlinear models. We'll come back to these a little bit later, but right now we're focusing on the linear ones. So what have I got? I've got a y, which is a function of a, the intercept, okay, so, which I add to every point, and each point is determined by where I am on the x-axis and the slope, okay, and b. So I have a predicted value. So I have here, by having a model, I'm basically extending a line to areas where I don't have points. Okay, so I'm interpolating or extrapolating away from my points. So even where I have points, I've fit a line, and now I can have a continuous predicted value. So my predicted value, which is why it has this little funny hat, is based on this model. Now I can see the model here. This is a line. I can see that it's not a perfect prediction, but it's based on some slope and intercept. So remember we spoke about the flood velocity versus the ebb velocity. So when water comes onto the marsh, it comes in with a certain velocity. When it leaves the marsh, it leaves with a certain velocity. Sometimes we have a higher tide, sometimes we have a lower tide. When it's a higher tide, velocities are faster. We have more water to move onto the marsh and more water to take off the marsh in exactly the same time frame, right? So it makes sense then that the flood velocity and the ebb velocity of each tide, and each point is a tide, are linked. Okay, so we saw earlier there's a significant correlation here. It's pretty high. It was, I think, 0.7, and it's positive, so there is a linear relationship here. What would it look like if I modeled it in a regression model, where y, flood velocity, is a function of ebb velocity, and then when I have that model, I can actually fit. I can predict what's happening in these gaps. So here's what it would look like. This is my Excel spreadsheet or a CSV file. And here are all the velocities, okay, for each tide. Each tide is a row, each point is a row. And here are my ebb velocities, and I can call one x, okay, x. Now remember, the equal sign is exactly the same as having that little arrow pointing left. And I can take tide is my data set, and I'm taking this variable, max ebb velocity, and y I'm calling max flood velocity. And here is my linear model, and I have a linear model of y as a function of x, so flood velocity as a function of ebb. And when I hit enter, this is what I get. I get a slope of 1.435, and I get an intercept of negative 0.17. So it's very close to 0, which makes sense. But I mean, like if we extended that line down, we would come here, and this is the slope. So this is the equation. Flood velocity, if I want to calculate a flood velocity, any flood velocity, all I need to know is the ebb velocity and these two parameters, the slope and the intercept. Okay, so here they are, and now I can add to my plot. Here's my plot from before. I plotted the data, and I can add an AB line, A and B, coming from slope and intercept, AB line of this linear model. And this is what that linear model looks like, this dot here. You can see that my blue dots, my real measurements, are actually falling quite well on the line. And this is what we call the goodness of fit. How well does this model describe these points? So I can predict y from x using the model. So I can tell you now that if ebb velocity is 0.65, then flood velocity will be 0.75. But what's my confidence around that? How do I know whether this line is worth anything, right? So I can see visually that the line is actually describing the points quite well. This model is a good fit. But what I can calculate is the what we call the error of the model. There's a residual, okay? You can call it, it can come from noise, natural noise in the data. It can come from other factors, like maybe during high wind conditions, the tide gets pushed off faster, and it has nothing to do with the ebb velocity. You know what I mean? So there could be other factors there. Or there could be errors to do, so noise in the instrument, errors in the measurement, I mean error in nature, right? So we have, what we have in this model is actually a collection of x's and those factors, plus some sort of error around the model. So when I fit the model, okay, when the computer fits the model, what it's trying to do is minimize this error. So say I've put that line over here, you'll clearly see there's a big error in fitting the line. So what I'm trying to do is create the line of best fit. So how does fitting the line work? It's done in a way to minimize the total error. We have a line of best fit, and what that means is that when I've fit it to my data, the sum of the squared residuals is minimized, is the least it can be. So first of all, I have a point that the line has to cross through, and that point is the mean x and the mean y. So from all these values, I can take all the ebb velocities, all the flood velocities, the mean of each one makes this new point. This point here, and the blue line, my model has to fit through that point. And from that point, now I'm just tinkering with the slope. And I tinker with the slope and with the intercept, okay? I can move it up and down, or I can kind of turn it around. And I do that because what I'm trying to do is to get these residuals, these distances between the points and my model to be minimal. So I play until the sum of all these differences is the lowest it can be.